Hello, Dr. Mateki back here with some thoughts on Chapter 9. So in this chapter, we add two components to the Solow model that are very important for understanding a more realistic growth model. So we're going to relax the assumption that the population is not growing. In other words, that the number of workers are changing over time. And we're also going to add technological progress. So this unit also goes into the golden rule once again and endogenous growth models. So for both of those last two topics, the golden rule and the endogenous growth models, I'm more concerned with the conceptual understanding and the implications for policy. Not that concerned with solving problems related to those two things and sort of parsing the model in detail. So for the exam that's coming up, just be very familiar with the entire Solow model and how to interpret different events and shift the curves and note the changes in equilibrium, be able to solve for the steady state mathematically, and answer a variety of graphical and quantitative questions related to the Solow model. So in order to account for population growth in the Solow model, we're going to add another parameter to the model, this n here. So n is just the growth rate of the labor force. So population and labor force are not exactly equivalent variables, but it's a good proxy to understand how growing population impacts production. And so n is simply the growth rate of the population. So typically it would be 1 or 2%, 3% per year historically. In advanced economies, now we actually might have to consider negative growth rates. So we have some populations are actually shrinking. But this, don't be confused by this delta L over L. This is just the formula for percent change. So n is a percentage. It's going to be entering into the model in the form of a small decimal, 0.01, 0.02, 0.03, something like that. Now remember, we are talking about capital per worker in the Solow model in terms of the key input into the production function. And so when we think about the amount of capital per worker, now we have two forces that are tending to decrease the amount of capital per worker. We have depreciation, which is a holdover from before, so machines are wearing out, so we have to replace those in order to maintain a constant capital per worker ratio. But now we have more workers. So if we don't add capital and we have a growing population, a growing labor force, then the amount of capital per worker is going to be decreasing. So in order to keep the level of capital per worker constant, we have to account for two things now. We need to replace worn out capital in the amount of delta K, and we have to produce enough capital to equip the new workers with capital in the amount of n times K. So if we were to distribute this K times delta and K plus N, that's exactly what we have here is these two terms. So if we didn't replace these two things, then the capital stock would be spread over a larger population, and so the value of capital per worker would be decreasing. This leads to a new equation of motion for the stock of capital per worker, little k. So delta K, remember this describes how the capital per worker, the stock of capital per worker changes over time. It's going to increase if investment is greater than break-even investment. It's going to shrink if this term here, the second term, the break-even investment is greater than the investment. So actual investment is still the savings rate multiplied by output. So S is the fraction of our output that we are saving and investing. And delta plus N times K is the amount of capital we need to have in a given period to make up for depreciation and population growth. So when these two forces are exactly in balance, actual investment and break-even investment, then delta K is equal to 0. So in other words, the steady state amount of capital per worker now is going to be the amount of capital where S times F of K minus delta plus N times K is equal to 0. Now the nice thing about this is it doesn't really change our diagram at all, and it doesn't really change the process for solving for steady state. We're just adding another number into the mix here. So notice that our investment function stays exactly the same. So this investment function is still S times F of K, no change at all. And this break-even investment here, instead of delta times K, it's now delta plus N times K. So the slope is getting a little bit bigger, right? So this coefficient on k is getting bigger. So this line is going to be rotating a little bit. But other than that, it's exactly the same. The intuition is still the same. The steady state is still the intersection of these two curves. Anytime we are below steady state, we are going to tend to approach it and move towards the steady state from left to right. If we start off to the right of the steady state, then break-even investment is going to be larger than actual investment, and the capital stock will decrease and force us this way. So no matter where we start, we are going to end up here at K star. So now what I'd recommend you do is sort of think in your head like, all right, so if one of these parameters changes, what is going to happen to the steady state? So for instance, we already know what happens if delta goes up, we know that K star is going to go down. Because if delta goes up, then this break-even investment line is going to rotate in this direction. Steady state is going to, equilibrium point is going to move to the left here. The intersection will be down here, and K star will decrease. And if depreciation goes down, the exact opposite will happen. K star will increase. But now let's look at what happens if n changes. If n changes, right, the nice thing here is the intuition is exactly the same. If n changes, then this coefficient gets bigger, the slope gets steeper, and this line rotates to the left towards the y-axis. It's the exact same impact of an increase in depreciation. So an increase in n will cause K star to go down as well. If n goes down, then the exact opposite will happen. This means that K star will go up. So the intuition might be a little funny here, but the increase in n makes it harder for us to maintain a given steady state level because we have to equip all these new workers with capital. A declining population actually makes it easier, right? So the amount of capital per worker is going to be increasing for a given amount of capital stock. So if you at first blush it looks a little bit confusing, but I think if you think about what a growing population means for the ratio of capital to labor, then it's going to make sense to you. And just a quick follow-up, this slide illustrates exactly what we're talking about in the previous slide. So if n increases from n1 to some larger value, n2, the break-even investment line is going to rotate out to the left towards the y-axis. The new intersection of the break-even investment and the actual investment line is down and to the left of the previous one. So we drop down to the x-axis and see that K star 2 is lower than K star 1. So an increase in population and the rate of population growth has caused a decline in the steady state value of capital per worker. So if you're ever sort of confused about how a given change will impact the steady state, then sketching out this diagram is a great way to do that, right? So it is intuitive if you sort of use the model and let the curve shifting and the new intersection point tell you what's going to happen to the steady state value of capital. I wanted just to spend a few seconds talking about the alternative perspectives on population growth. And so this is a common misconception that some people still talk about today. And so this is the Malthusian Model, a couple hundred years old. But basically, Thomas Malthus was sort of political economist, sort of scholar that predicted that population growth will outstrip the Earth's ability to produce food. And so that population growth will lead to basically the destruction of humanity, right? So some very, very dire predictions. However, this never came to be. So since the time of Thomas Malthus, world population has increased a ton, and yet living standards are higher than ever. And it turns out that until we achieved a fairly high level of population density in cities and things, we didn't really see a big increase in the standard of living. And so this whole story of population growth causing overcrowding and overconsumption of food and that sort of thing, what is this forgetting to take into account? It's technological change. So our ability to produce food has increased dramatically. So the same amount of land can produce many, many times over the amount of food that we could before with modern farming techniques and genetically modified seeds and all sorts of different technological advances. So if we're talking about a static world, then yes, if resources are staying constant, then more people that's going to cause a problem. But the reality is that we have the ability to create more from the same amount of inputs with technological change. And we'll see coming up here that technological change is really the key to understanding how we can achieve consistent growth in the standard of living over time. At the opposite end of the spectrum is a more modern interpretation of population growth, the Crimerian Model. So the idea here is that population growth actually contributes to economic growth. So more people means more geniuses, scientists, engineers, and so these sorts of people are going to be key in driving technological change and driving us forward. And so there is a lot of empirical evidence supporting this. So as world population has grown, so did the growth in living standards. Regions with larger populations have enjoyed faster growth. Dense cities have been areas where ideas flourished and technology has spread very quickly, disseminated into different applications. More population is more opportunity for specialization in trade. There's just all sorts of different channels through which this increase in population can lead to faster economic growth. But the key is it's this process of learning how to do things better, more efficiently, creating new types of machines that can help us produce faster with less work, with less labor. All these sorts of things happen when we have more people involved in the process. And the final piece of the puzzle that we need to talk about in chapter 9 is technology. So in the Solow model of chapter 8 and the beginning of chapter 9, actually, the technology is held constant. So we have a production function that just sort of has the technological component inherent in the function. And so when we have this sort of model, we end up with a certain capital per labor ratio in steady state capital per worker. And so if the capital per worker in steady state is constant, this also means that output per worker is constant. So the output per worker, which you could also think of as income per worker, that's how we measure our standard of living in this sort of setup. So if our income per worker or output per worker, which in our model is little y, if that's not changing, then our standard of living is not changing. You could also think of it as in steady state, we're going to approach a certain level of consumption per worker. Consumption per worker is another way to think about standard of living. So if our consumption per worker is not increasing over time, then we're not increasing our standard of living. So neither of these things is true in the real world, right? So we have lots of evidence that technology is constantly changing. And data shows that income per capita income, per capita GDP, if you want to think of it that way, that's not changing either. That's not being held constant either. That's changing. So on average, U.S. Real GDP grew by something in the order of 2% a year on average, and between 1950 and 2019, increased by a factor of 4. So clearly, we are better off than we were 70 years ago. So how is that true if the Solow model we've been looking at so far is accurate? Well, the thing we've omitted, just like Thomas Malthus did, is technology. So now that's what we're going to do here. And this is the final key to unlocking a model that really describes in a realistic way how an economy grows over time. In order to add technology to the model, we're going to have to add a new variable and a new parameter. So the new variable is E, and this is labor efficiency. So this is how productive a worker is. It's a measure of how productive or effective a given worker is. And so in this sort of setup, technology is, we can think of it as being labor augmenting. So technology helps workers become more effective, more productive. And technological progress happens when this variable E is growing over time. So if over time laborers, workers are becoming more efficient, then there's consistent technological process each period. So in this model, we are going to assume that labor efficiency grows at rate G. And so again, this is an exogenous parameter. It's not determined within the model. It's just a parameter that we would assign a value to given our observation of the way the world really works. So now the production function has a new variable. So the amount of output that we can produce is now dependent on capital, the amount of capital we have, the amount of workers we have, and how efficient those workers are. So L times E, we can think of this as the number of effective workers. So if you're an astute observer here, you'll notice that an increase in E is the same functionally as increasing the number of workers. So increasing a worker's effectiveness is like having more hands to do the work, more workers, but you're not actually increasing the number of workers. The ones you have are just more productive. But mathematically, it has the same exact effect on output, on Y, GDP, as increasing the labor force. This is a part where people tend to get tripped up a little bit in this model. So once we're talking about effective workers now, the notation changes a little bit, and what these variables represent, the little y, little k, etc., what they represent is a little bit different. And so in order to put the production function in per worker terms now, we're actually going to divide by L times E instead of just by L. So we're putting all of the variables into per effective worker terms now, not just per worker terms. So little y is now aggregate output, big Y, divided by L times E. Little k is now aggregate capital divided by L times E, etc. Same for consumption per effective worker, and on and on. So once we go through the same process that we went through in Chapter 8, the the per effective worker production function looks exactly the same. So it looks like something identical to what we've already been working with. Little y is equal to f of little k. However, this little k, we have to keep in mind, is now defined slightly differently. It's k divided by L times E instead of just k divided by L. Savings and investment per effective worker look exactly the same, but again, we have to realize that y is now y divided by L times E, and k is now k divided by L times E. So a bit of good news, the way that we can use the model graphically and mathematically changes very little when we add technological change to the mix here. So we still have break-even investment in this setup. We still have the amount of capital that we need to keep the amount of capital per effective worker constant. We just now, instead of having delta plus n, we have delta plus n plus g. So again, we're adding another small number here. So g, is going to be something on the order of 1, 2, 3% typically in these sorts of problems. So g might be 0.02, n might be 0.01, and delta might be 0.04, something along those lines. Might be typical numbers. So break-even investment, delta plus n plus g times k. What this consists of, we break it down into these different terms. If we were to distribute this k, we'd have k times delta, k times n, k times g. So we need delta k to replace the worn out capital, n times k to provide for the new actual workers, and we need g times k to provide for the new effective workers that are created by technological progress. So these are not actual workers. Again, this is just the modeling technique that we're using to account for an increase in productivity. So we're essentially adding new workers without actually adding new human beings. Again, the good news here is that the graph and the mathematical technique that you would use to solve for steady state is exactly the same as we've seen right along. So our law of motion is changed only slightly. So delta k is equal to s times f of k. This is unchanged. But now we are going to subtract delta plus n plus g times k. So in steady state, delta k will be equal to 0. So in steady state, actual investment is just equal to break-even investment once we account for this parameter g. So again, if we were going to solve for steady state, we would just take our production function, the parameter s, these parameters which will be given in the problem, and we will set actual investment equal to break-even investment and solve for k. The process is functionally identical to what we've done before. If we want to use the main Solow graph, exactly the same as what we've done before. Again, we just have another little parameter here, g. So again, try to think about what's going to happen in the diagram here. The only little trick that you need, or the only little difference you need to understand, and this is important, the x-axis is now capital per effective worker. It's not capital per worker. So what's going to be constant in steady state is capital per effective worker. However, as we're going to see here, even if capital per effective worker is constant in steady state, capital per worker in the actual capital stock is not constant. So we're actually increasing capital over time to account for the technological process, the effective workers, and so that implies that we're actually going to have an ever-increasing ratio of capital to workers, to actual workers, which will lead to an ever-increasing amount of output per worker, income per worker, those sorts of things. So this G, it turns out, is going to be the key to unlocking persistent changes in the standard of living. So back to the diagram here, though. So we can see that whether we increase delta N or G, this has the exact same impact on the steady state. So an increase in delta N or G is going to rotate this line to the left towards the y-axis, and it will decrease the amount of capital per effective worker in steady state. So again, the key is recognizing that in this setup, we're talking about capital per effective worker, not capital per worker. So that might be counterintuitive at first because we're talking about G being, the secret to growth, and it ends up, if we have an increase in technological process, it reduces the capital per effective worker in steady state. That does not mean that we are decreasing the standard of living. It actually means that we are going to be increasing that over time. And so that's something that we can see more easily in the spreadsheet example, I think. And so I'll have another short video going over the Excel spreadsheet example so you can see exactly how all of these different variables change over time. Understanding this chart given in your textbook is extremely important for understanding the intuition, what's happening here to all these different variables. If you can understand exactly what's going on in this chart, you have a good handle on the Solow model. So we're talking about the Solow model with technological progress here. So we're talking about E being in the model, and so our small letters are now the per effective worker values. So what happens to capital per effective worker in this model in steady state? Well, in steady state, right, the definition of steady state is that little k is not changing. So the growth rate is 0. So capital per effective worker, or K divided by E times L, is not changing. Output per effective worker, little y, right? So remember, little y is a function of little k. So in other words, it's equal to f of little k. So if capital per effective worker is not changing, then output per effective worker is not changing. To help sort out the last two items here, the output per worker and total output, we're going to use a couple of shortcuts. So remember, the percent change in the product of a variable, of two variables, so in other words, the percent change of x times y is approximately equal to the sum of the growth rates. So percentage change in x times y is approximately equal to the percentage change in x plus the percentage change in y. We could also do the same thing for division. The percentage change in the quotient is approximately equal to the difference in the growth rates. So if we're looking at this line here, this output per worker, let's think about first what that means. So output per worker, GDP per capita, that's the exact same thing. So output per worker or GDP per capita, that's typically how we measure the standard of living. So how much stuff are we producing per person? So output per worker in this model is defined as big Y divided by big L. So this is aggregate output, total output divided by the number of workers. Based on the definition of output per effective worker, we can say that output per worker, Y divided by L, is equal to Y times E. We can get that by taking the right-hand side of this definition here and multiplying by E. So if we multiply this, the right-hand side by E here, it's going to be E divided by E, and this is just going to turn into a 1, and it's going to go away, and we'll be left with Y times L. So we get this expression here by multiplying both sides of this expression here by E. So Y divided by L is equal to little y times E. So now we can figure out how much output per worker is growing in steady state by examining how much these two variables are growing in steady state. So output per effective worker we know is not growing. So let's skip down here actually. So I'm just rewriting this from above. So aggregate output divided by total number of workers is our output per worker. You can think of this as GDP per capita. This is equal to output per effective worker times E. This is approximately equal to, by this shortcut, the percentage change in output per effective worker plus the percentage change in E. So in steady state, we know that output per effective worker is not growing, so that's 0. And by definition, E is growing at rate G. So now, in steady state, we actually have growth in output per worker, GDP per capita. So the standard of living is increasing, in other words, at rate G now. So each period, we are increasing the amount of stuff per person that the economy is producing. So if we were to look at total GDP in the economy, so that would just be aggregate output, or big Y. How much is this growing in steady state? Well, by using the same sort of logic here, so in order to get this expression here for total output, we're just going to multiply both sides of this expression by L to isolate the Y. So we're left with Y is equal to little y times E times L. And so if we use the same shortcut, we can figure out how much this right-hand side is growing. And so we can break it into the percentage change in little y plus the percentage change in E plus the percentage change in L. And so again, this is 0 for the output per effective worker. The technological growth is rate G, and then we add that to the growth in population, which is N. So total GDP is growing at rate G plus N. And so if you think of something like growth rate of 1% for the population, 1% population growth rate, 2% growth rate in technology, then what we'd expect to see is per capita incomes growing at about 2%, and aggregate output, or GDP, is growing at about 3%. And so those numbers line up pretty well with what we've seen historically since about World War II. And that wraps up this video. Thanks for listening. And again, always let me know if you have any questions or like to talk about any of this stuff in more detail. Thanks.